Hello everyone, welcome Adam Times again, and my pleasure to welcome you to one more session where we will explore neural network architectures for sequential data. So this is the first out of 2 lectures in which we're going to examine a new type of neural network, recurrent neural networks in particular, and as the title of this session suggests, this specific type of architecture, these recurrent neural networks, are a handy tool whenever you face sequential data. So let's see what they can do for you. The lecture is organized in 3 sessions. We'll first of all introduce sequential data and talk a little bit about exemplary applications and, importantly, the challenges that we typically face when working with sequential data. We will subsequently have a look into language models. This will be our first contact with data in the form of natural language, text. As it turns out, text data is one example for data with a sequential structure, and we will use the example of language models in the following to introduce recurrent neural networks, and they represent the third and last core part of this session before we end with a brief summary. All right, that is pretty much our agenda, so let's get going. What is the business case of sequence data or sequential data or temporal data as a specific form of sequence data? This is pretty much the scope of this part. And in general, we can agree that data which exhibits some sort of temporal ordering or a sequential structure is omnipresent. We have it everywhere. If, for example, you are involved with forecasting the sales of some good in a shop or of the product from a manufacturing company, sales typically exhibit a seasonal pattern, where maybe sales are a little lower in summer and then peak sometime in spring and or fall. We call these patterns where the magnitude of our sales time series always shows highs and lows at specific calendar days. We call such a pattern a seasonal pattern. Or if you think about the business cycle, where we typically see situations that ups are followed by downs. Also, if you think about your shopping behavior, certain products you might need every week, maybe every week you go shopping buying some milk, which you then consume over the course of the week. Whereas for other products, say shampoo or something, that just use a little longer, which you consume over a longer period. You would not buy these products every week, you would buy them maybe every 3 weeks or every month. But in either case, there is a certain period in which you buy these products. And because of that, your individual level purchase behavior exhibits a certain temporal pattern. Every week you buy your milk, every month you buy your shampoo. There are many more examples, maybe not explicitly geared toward management. Just think about the words in a spoken language. Clearly, we have a grammatical ordering in our sentences in natural language. And this ordering enforces a temporal pattern in the words of a sentence, for example, or generally the words of some text of natural language. They follow a certain grammatical syntactic ordering. And for that reason, we can think about text as sequential data. Or even more intuitively, think about the scenes in a video that you watch. Whatever you see in a scene, whatever is going on, what the main actress is doing right now, it will depend on what she has done before. So there is an ordering. This is what I'm saying. The scenes that you currently watch, whatever is happening there, it depends on whatever has happened before in that movie. So again, there is an ordering in the data that you are working with. And you can come up with many more examples, I believe, where you are working with data that exhibits some sequential structure where there is some time ordering, for example. So it's actually very common to work with such data. Panel data is just another example. You might have worked with that in your econometrics classes. And the point that is noteworthy here is that any type of data that exhibits temporal dependencies, or that is sequential, by definition, this data violates our IID assumption. Temporal data is not independent and identically distributed. The observations in a time series, these observations, they are not independent from one another. Quite the opposite is true. We typically believe that in a time series, one observation, maybe the sales that you observe today, is dependent on sales that you observed in previous time steps, maybe yesterday or the day before yesterday. Right, and this temporal dependency is what violates the assumption of independence, which is an issue simply because many of the statistical tools that we are used to working with, just think about your regression model, they assume that data is IID. And whenever it is not, you must not use these tools. You violate their assumptions. In the best case, statistical tools would not give you the best possible answer. And in fact, it might be, if you use an inappropriate tool to analyze sequential data, that the answer that you are getting is strictly wrong. So we need new tools. That's the main take home here. For temporal data, because the data points are not IID, we will need specific tools. And this session is about introducing some of these tools that we can apply. And in order to better appreciate that, it might be useful to have a specific example in mind. And since many of us have an econometrics or econ background, economics background, a popular example of temporal data, I believe, is that of stock data. So let's look at some financial data. And here we see the German stock index and its 27-year historical chart and how it developed, with many ups, sharp ups, but also very sharp downs. One very sharp down indeed just recently. So this is data up to March 2020. And you certainly know where the big drop that you see at the far right side of the picture, where that is coming from, and how it has basically crushed all the progress that has been made over years. But anyways, if you believe, or if you have an interest in predicting stock prices, and if you believe that predicting stock prices is at all possible, then you will also believe that the stock price, or this index value that we see at a certain day, depends on past prices, at least to some degree, which might then allow you to forecast future price or future index developments. I will soon try that out. Without much success though. Spoiler alert, this is not an attempt to give advice how to invest in the stock market or how to trade. It is just an example. My focus is sequential data, and indeed stock market data certainly is sequential. It's a time series, a financial time series, and will serve us as a good example. I'm more interested in the statistical tools that we can use to model such data. Where, and I cannot stress it enough, bear in mind, predicting the stock market is really hard, to say the least. Statistical tools. First of all, let us try to introduce some notation. Let's say we have a variable in which we are interested and we denote that by x. And you see this index t here. Normally I've been using I as my index whenever it came to indexing data points, like different customers or credit applicants, for example. I was always denoting them as xi, and I was the index of the observation. And now I changed that. For temporal data, it's common practice to use the small t as an index for temporal or for point in time. This is how you can think of it. And then xt is one unit, 1 point of observation of our variable x at a time point t. So for example, it could well be that xt is the closing price of your favorite stock, maybe Microsoft, maybe SIP, whatever stock you're interested in, maybe Mercedes. Closing price of some stock at day t, or at trading day t to be precise. And then if we try to predict that stock price, the closing price of our favorite stock at day t, what data would we use from which to generate predictions? Well, many things might come to mind. The maybe most intuitive type of data we could use for that purpose are past realizations of our time series, so past prices. xt minus 1, for example, if xt is the stock price, let's say we are predicting Microsoft. So let's say xt is the stock price, the closing price of Microsoft today, then xt minus 1 would be the closing price of Microsoft yesterday. And xt minus 2 would be the closing price of Microsoft day before yesterday. And it continues like that all the way to some value here, x1. Now what is x1? Well, strictly speaking, x1, this guy here, that's sort of the origin of our time series. Well, in a stock forecasting setting, that's maybe ill-defined. What is the origin of the Microsoft stock price time series? Question mark. Is it the point in time where Microsoft was first listed at the stock market? Or is it simply the point in time that from which you started downloading a snapshot of the stock price time series? What actually is x1? Generally, this is the origin of our time series. What really means origin of the time series depends a lot of the specific task. And if we go to a website like Yahoo Finance, for instance, and we download the last 27 years of stock price data, as I did in order to do this chart of the German stock index, then, well, 27 years ago, that would be my x1. It's probably a good idea to think of it as the starting point of your data, of your analysis period. And that already hints at one of the key methodological issues here with sequential data. This T might be somewhat ill-defined, or if we want to have a model that forecasts not only the stock price of Microsoft but multiple stock prices, which would be very useful for trading for portfolio optimization. It's good to think about one stock, but as a portfolio manager, we would want to anticipate future development in multiple stocks and indices and financial instruments. And the thing is that the length of our sequence, so the period from point t over t minus 1, t minus 2, etc., all the way back to time point 1, this window is of a variable length. Maybe sticking to my stock price example, of course, some stocks appeared much earlier on the stock market than others. the stock of Google or Facebook, for example. If you compare them to Chrysler or Johnson & Johnson, these stocks appeared a lot earlier of the stock market. So if you want to build a model that forecasts all the stocks in the S&P 500, for example, the time periods would differ a lot. And in a statistical model, it's not so easy to handle sequences of varying length. And in fact, you will see that this is also the case for recurrent neural networks. And because it's complicated, the question arises, how could we make computations tractable? If you feed the formulation xt, or the probability of observing a certain closing price at day t, xt, we state that it depends on the previous closing price, xt minus 1, and the closing price that day before, xt minus 2, all the way back to the origin of our time series. How can we compute that if time series are of variable length? This is going to break pretty every statistical tool, or at least many, and there are two ways to address that. And the first way is to just truncate your time series. Maybe we do not need all the past information, t minus 1, t minus 2, etc., up to t1. Maybe we don't need them all to predict xt. And in fact, that's quite plausible. If you are interested in predicting the closing price of Microsoft today, you would not believe that in a model you need the closing price of Microsoft 10 years ago. You would not believe that a closing price that was observed 10 years ago has much to do with the closing price of today. It's outdated, right? It's not relevant anymore. So probably, although we could get the closing price 10 years ago, we would not need it in a model that is to predict today's closing price. It's outdated after all. So truncation of our time series, that should be a good idea, and it shouldn't harm us, provided we pick a suitable threshold. And this threshold I denote by tau. So in my notation, our model that gives us a probability forecast for observing xt, we can write it down as a function of probability of x1 times the probability of x2 given x1. If there is temporal dependence, then x2 will depend on x1, and we explicitly spell that out here. And then for the next data point in the series, x3, it will depend on x2, but also on x1. So the temporal dependency extends and now encompasses the first two data points. And this window of dependence, maybe this is a good way to think of it. So let's write that down. So this is my window. It's a time window after all. My window of dependence that grows a little bit up to a certain point, which I denote by xt minus tau. Note the ordering. So we have in these conditional probabilities, we have the probability of x3 being dependent on x1 and x2. So if we extend that series, the probability of xt, we write it down, or we assume it depends on xt minus tau plus 1, xt minus tau plus 2, all the way up to xt minus 1, which is just the data point right before xt. So xt minus 1, again, that would be e.g. price of yesterday, and it was certainly a better idea to write it here where I have no space, and xt minus tau, maybe that could be, depending on our setting of tau, price 5 days ago, if we set tau to 5, right? And you see the graph, or you see this directed graph at the lower part of the slide, where I write down the sequence of x1, x2, x3, x4, x5, and x6. And the arrows indicate dependencies. And the blue arrow shows that I make, or I assume, every data point being dependent on the previous realization of my random variable x. So the blue arrow says that x2 depends on x1, and it says that x3 depends on x2. And if I believe that setting tau to 1 is enough to have a good approximation of the temporal dynamics in my data, then we can call our model a first-order Markov model. This window of dependence that translates, or that equates to the Markov assumption, where we basically state that a data point is dependent on the tau previous data points. And if we set tau to 1, we obtain a first-order Markov model. And if we set tau to 2, for instance, we obtain a second-order Markov model, which is also shown here if you take the green arrows and the blue arrows together. So if we make a second-order Markov assumption, we would believe that the value, the realization of x3 depends on both x2 and also x1. And, well, we could also depict a third-order Markov model, and I will use purple for that. This would basically say that the value of x4, if we stick to this example, currently it depends on x3, and it also depends on x2, the value of x4, and if we make it also dependent on x1, we further extend the temporal dependency, then we would obtain a third-order Markov model, right? And then, of course, in a third-order Markov model, x5 would also depend on x2, and x6 would also depend on x3. Here we go. So, in a nutshell, one way to handle our sequential data is to consider a fixed window of dependence and then state that a data point xt depends on the tau previous realizations of the random variable x, and use that data to build your model. And we'll soon try that out. This is called an auto-regressive model because we regress our random variable x on previous realizations of itself. We regress x3 on x2 and x1. That was one of two approaches. The other is a class of statistical models that are sometimes called latent variable models, or they are also called state space models. And the second, or well, both these terms, latent variable or state space, it originates from the fact that these models have a sort of memory. They keep track of all past observations in a way, but selectively. So in a way, they selectively keep track of the entire time series all the way back to x1 in a sort of memory, or in a latent variable, in a variable that is not directly observable. And I denote this latent variable by ht. And then we have our notation where we state that the probability of observing some value xt, closing price of our favorite stock today, where it depends on the previous realization, so yesterday's closing price, xt minus 1, the blue part here, and also our latent variable ht, or, well, yh, we will soon refer to something, or this variable, as the hidden state. In a recurrent neural network, we use the term hidden state And I believe this is why the symbol H is a popular choice for this latent variable or this hidden state. And let's start with the upper part of the graph that resembles the previous plot, but you see that now our graph is fully extended, and I have every data point being dependent on all the previous data points or all the previous realizations, and this is why it's looking a little bit cluttered. X6 is a good example. In X6 we have X5, we have the dependence over the blue arrow, that is xt minus 1, so the previous realization, but we also have the value of X6 depend on X4, that's this arrow here. I'm just sketching it so that you can make sense of this graph, and we have a dependence somewhere, I believe, and it's even hard to find it, to be really honest. Well, we definitely have this dependence here on X2, and we have this one here, and we would have one more arrow connecting X3 to X6. It's probably just behind some of the error arrows, but you would have that as well. So essentially, we don't model these green arrows explicitly, because then our computation would be intractable, or we would have this issue of sequences of varying length. We don't really go back to the origin of our time series when we model or try to predict X6, but we have this latent variable that accumulates over time. That is, memory is a good way to refer to that. We have this memory, and it sort of summarizes everything that has happened before in this time series, and we can use it to predict the next value of the time series, the next realization. And given that the upper graph, which is only to resemble our auto-regressive model, is a bit hard to appreciate, a better way of looking at it is the lower graph. It's the same picture, it's just a bit more tidy in a way, where we spell out how we believe our time series to evolve, and where we also make explicit how the hidden state or our memory evolves over time. And I really encourage you to think a little bit about this lower picture here. It's quite insightful. We have the temporal evolution of our time series from x1 to x2, x3, x4, x5, x6, always with the direct explicit dependence on the previous realization, xt minus 1. And in addition, we have every observation being dependent on the memory or the hidden state, which is the green arrow. And then we have the evolution of the hidden state that is updated over time, whereby it depends on the previous hidden state. It's like a memory. And from a memory, like human memory, you add to it, if you read a good book, for instance, or you read a nice paper, or you read a nice blog, you add something to your memory. And at the same time, you would also occasionally delete something from your memory. So that happens a lot to me when I'm trying to remember things, like tasks I should do at home. Then this deletion from memory is something that I know very well. Maybe you experience that yourself. And this is the yellow arrow here, this updating, where we have a dependence of our memory at a certain point in time being dependent on the previous state of our memory, but also on the previous realization of our time series, which is the red arrow. And if you think about it, that makes a lot of sense. So the red arrow, that makes a lot of sense. We have our memory, our belief, or how the time series develops, what we have seen before. And whenever we see a new value, we are in time point 3, for example, and in time point 3, we know what has happened in time point 2, and we consider whatever happened in time point 2 in order to update our memory, to update our beliefs, how the time series evolves, what the temporal pattern in the data is like. Yeah, so the second equation here, which basically states the evolution in our memory, also makes a lot of sense. We call these models latent variable models, where then H is our latent variable, or sometimes, as I said, it's called a state space model, where we have this latent states H that evolves over time. Right, so a little interim conclusion. Sequential data violates the IID assumption, which is why we need specific statistical tools, and we have seen two of them. We have seen the auto-regressive approach, where we just define a window of dependence, tau, or I denoted by tau, and then say that it is possible to model xt as a function of the previous tau realizations of the time series, xt minus 1, t minus 2, etc., all the way to xt minus tau. That's the auto-regressive approach that we could use easily with regression, neural networks, or any type of machine learning model. And this is what we do next. In addition, we have this latent variable or state space modeling approach, where we keep this memory that summarizes the whole time series, or in theory it could summarize the whole time series, and we use this memory to predict future values of xt. But they both these both approaches, the latent variable model and the auto-regressive model, they both serve the same purpose, which is giving us an estimate of our time series, or giving us a tool that we can use to model sequential data, the joint probability, and this is what, note that, right? So here, that's a joint probability, and this is what we are ultimately, what we are interested in, modeling this joint probability of the entire time series. But it's hard because of the varying length that we might have to cope with. So we use an approximation, and you have seen two. The auto-regressive one, the latent space one, or latent variable one, but they both are to approximate the entire conditional probability or conditional likelihood function that you see here, which is just hard to work with, hence the approximation. And I want to conclude this part with a little introduction, or no, sorry, it's not really an introduction, it's more of an example. And the code for this example is available in GitHub, but honestly it's just an adaptation from Dive into Deep Learning, very close adaptation, or hardly any real adaptation. I just recoded that to make the code easier for you to access if you want to play with it. All the credit certainly goes to the colleagues from UC Berkeley who contributed this great resource, Dive into Deep Learning. Anyways, what have we got here? We are just generating some artificial data for 1,000 time points. So note my variable t, which is just the sequence from 1 to 1,000. I consider these time points, and then I create a variable x just by adding a little bit of random noise and using the sign function, which gives me this nice cyclical behavior in my time series. Clearly x is the value of t, and clearly we could approximate x easily using the sign function, as it's just the sign function that we use here. But any type of machine learning model that we throw on this data set would not know that all we need is the sign function. This is how the data looks, and the ups and downs, this is because of the random noise that we are adding here, right? Note this part. Otherwise, we would just obtain the sign function. And we are trying to predict this time series with a feed-forward neural network, a tool that by now you know very well, which requires us to think carefully how we set up our input And this is the next step. Note my variable tau here. Tau equal to 4. Well, 4 is arbitrary. I just picked 4. You could just play with these values if you wish. I call it the embedding dimension for the auto-regressive model. That's certainly a big term, embedding dimension. If that doesn't ring a bell, no worries, we're going to get there. It's just the window of dependence. That's much more intuitive, this terminology. It's my window of dependence. And then in this little loop here for I in range tau, I'm creating my feature matrix and my labels. And you see that exemplified here. So have a look at this matrix. These are my temporal data points. First of all, let's use red for the target, for the modeling target, our dependent variable. And note how I have my modeling target in this matrix. I have it in this matrix. I have it in the first column. So that is actually my target. Okay. And my features, let me use blue for the features. Features or my independent variables, you find them here in the matrix. These are my features. And then these indices, out of a sudden, they make perfect sense. It was not meant to give the indices in this matrix. What I'm trying to say is, look at the very first, I should use a different color really. Let me use black. So look at the first row in my matrix. There we are basically saying, I want to forecast the value, the stock price maybe, at day 5. I want to forecast X5 using data from the 4 previous days, X4, X3, X2, and X1, which are my independent variables. Let's say today is day 4, or let's say today is day 5. I have seen all the prices of the last 4 days. I've stored these stock prices, and now I want to predict what is the closing price of my favorite stock today. And I don't know when you are watching this video, I'm assuming that the stock market is still open and that this example then makes sense. And for the next day, X6 essentially, we shift our window of dependence by 1 forward in time. So our features to predict X6, X2, X3, and now I'm smiling, I wonder why, X4 and X5. It's actually quite odd if you're trying to make jokes and you do that to yourself. Anyways, let's get back to the stock market example. So, okay, we predict X6, or maybe just to be on the safe side, let's assume we predict X7. And to predict X7, we have X3, X4, X5, and there it is again, X6 as our inputs. You see the structure. So one more color would be nice. We always see how these arrows are just to highlight the structural pattern in our data, right? This is not to indicate some sort of dependence. I'm just highlighting how to read this matrix and how to interpret this matrix. And what you want to note here is that our data looks exactly as the data set we've been using so far in machine learning. We've been using data sets like this one in business analytics and data science all the time, and we've been using them in the tutorials where we played with feed-forward neural networks. This is exactly the tabular type of data set we've been working with so far. So we have broken up our time series into little chunks, where each chunk has 4 observations and the subsequent observation as our target variable. And that is in fact a standard approach how to deal with sequential data when you build an auto-regressive model. Well, And since we now have the same structure of our data as before, we can just use the data in the very same way as we did before. We can split it up into training and test. We take a couple of days to train the model, and then we try out that model on the consecutive days. Well, as you clearly see here, with temporal data, if you split it into training and test, you would not shuffle your data points. You would typically take them in their original order. So you might want to split them here and then say all the data before time point 7, including 7, that is my training data, and all the data points that follow time point 7, I take these as my test points. This is how you would train. This is how you would typically split your data. And this is what I'm doing in step number 3 in my code. And then you can just fit a neural network to that data. In fact, you could fit any machine learning model that you like to that data, and you could let it predict both the training and the test set, which is what I'm doing here. Note that my training set has 600 observations, which means that later on I'm drawing this line. So here we see our training window, where we basically have our forecasts in orange in sample. And here we have the test set of a test window, right? And this is because of this 600 here. If you haven't seen it, here you go, right? There is the 600. Okay, to the Python experts, don't be angry with me. If I index my data in this way, then data point 600 would not be part of the training set, it would be part of the test set. Anyways, what do we see? Well, I don't know what you see, but just by eyeballing, blue is the actual data, orange is our forecast. The model doesn't look too bad. It does quite a good job at predicting the next observation in our time series. And actually this makes sense because this time series is rather well behaved. It's just the sine function with some noise. The noise is random. So the task of our model is to understand that the data behaves in this cyclical manner following the sine function. And we make our model solve that task, or we let it try solving that task by showing it the past tau, which is 4 in my case, by giving it the past 4 data points. And from the past 4 data points, the model has to understand this sine function type of behavior. And just looking at that data, all looks well. Let's make the task a little harder. Let's say we want to do multi-step ahead forecasting. That means that we don't want to predict only the next day, like the next closing price or the next closing price. Let's say we also want to predict the closing price of tomorrow and the day after tomorrow, and maybe even the closing price of our favorite stock at the end of this month. So we predict multi-days ahead. That is a lot more challenging. And you can get a feeling why it is more challenging by looking at our data. The thing is that if we want to predict further ahead into the future, at some point we would not be able anymore to use xt-1 as an input to our model. Why? Because we don't know xt-1. If I want to predict the closing price of tomorrow, I don't even know today's closing price. But if my forecast target is tomorrow's closing price, and let's say it's just 1 p.m. It's 1 p.m. My forecasting target is tomorrow's closing price. I don't even know xt minus 1, which would be today's closing price. So I don't have access to this value, xt minus 1. And the more we walk into the future with our forecasting targets, the more prevalent this problem will become. And what you see in my matrix here is that at some point, as input to my model, and it starts when we try forecasting the value x7, this is just by construction that it starts at x7. For the data point t minus 1 and t minus 2, I do not have access to these values. If today I'm basically on day 5, 1 p.m., my forecast target is x5, that is what I don't know. But if I'm in t equal to 5, day 5, I have access to x1, x2, x3, and x4. And you see that if I'm further extending my forecasting horizon for predicting the value on day 8, I would have x5, x6, and x7 among my inputs, and even worse for x9, where all the independent variables are not actual observations of my time series, but model predictions, because this is the best assumption I can make. If I need these inputs for my model, then I can only use its forecast to predict x9, which means 4 steps ahead. Well, no, 5 steps ahead, strictly speaking. And this means that if my predictions are inaccurate, and remember all forecasts are wrong, just some are useful, that's what they say. If my predictions are erroneous, or at least have some error, then these errors will accumulate the farther I walk ahead in time. And it's nice to look at the graph. Here you have the red line distinguishing between the training and the test period. All is well in the test period. Sorry, all is well in the training period. And then what I'm showing you here is the multi-step forecast in green after the end of the training period. And you see, well, first of all, the thing that you will notice first is this part here, the flat part. That's probably what jumps to your eye the very first, where, well, the message probably is bad forecast, which is true. Very bad forecast. If you look more carefully, then you will also notice that shortly after the end of our training period, and again, this is where I'm creating this multi-step forecast, multi-step ahead forecast, very beginning, before our forecast turns into a flat line, we are able to predict this increase. This rise, we get it right. At least for some days. So apparently the neural network has learned successfully that we are in an upward swing with our time series or with our data set, and it basically projects this upward swing sometime into the future, but at some points the error in our forecasts accumulate and we don't have well, an accurate prediction of the trend of our time series anymore. And what you can also conclude from this example is that your model is using only tau equal to 4, is unable to really capture this cyclical behavior of the sine function. It it is not able to understand that at some point after going up, the value of x is also going to decrease again. Instead, our forecast turns into a flat line at some point. Now, what are the take-homes here? It shows the difficulty of multi-step ahead forecasting for auto-regressive models, because you need to rely on the model's own predictions at some point in time, which is problematic. And I invite you to play a little bit with the notebook. I'll have it open here, and I guess you can see it. It's available for you on GitHub. This is all the examples. I hope I've run that code, but I should have. That was the beginning. We talked about all that. You can play with that. Here's our multi-step ahead forecast. And well, I haven't shown you a slide for that, but at the end I'm also visualizing the multi-step forecasts for different step sizes. So it's a bit hard to see, I know. But for 4 steps into the future, that's the blue line. Okay, that's the hardest to see. Maybe we should start with the red line. That is a forecast 32 days ahead. So it's the most challenging example. But you see that for this case, the model still got it's somewhat right. At least we have this up and down pattern. That bit it got right. And we do not see this behavior of our forecasts getting or turning into a flat line. And we saw that before in the upper graph because we were just forecasting a long time into the future. I was basically attempting from day 600 onwards to predict all the next 400 days into the future. Think about that. In a stock modeling setting, that would be 400 days. That's almost 2 years I'm trying to predict into the future. What might be the closing price of Microsoft in 2 years' time? I mean, you would not believe that this is very possible or that can be accurately forecasted using any type of model. So this is why things got really bad here, and the lower graph is clearly worth examining, where you see that with only using some past realizations, but actually to get this nice graph, I was cheating a little bit. I increased my window of dependence, making it a little bit longer so that the model has more access to past observations, and then it is able to pick up this cyclical behavior from the data. Play a little bit with this. I hope the code is robust enough for you to not break it. It's the live video. No, it's not a live video, but it's a video. I don't want to ruin it, so I don't try it out. I will try after stopping. Let's go back to the slides. We are almost done. Here we go. Yeah, so what are the take-homes? We need special statistical tools to handle sequence data. We've seen two families or two branches in the statistical modeling toolbox. We've also seen some demonstrations for the auto-regressive approach, which you could use right now. Any type of machine learning model, even if you have never taken an econometrics class, for example, well, shame on you because you really should take econometrics classes, but say you haven't only taken business analytics and data science, all you know is machine learning. Even then, you could go and build auto-regressive models using neural networks and other supervised machine learning algorithms when using this approach to organize your data by considering past realizations, or sometimes they say lagged values of the time series itself. And what we will do next is familiarizing ourselves with the other approach, the latent variable approach, which is available to us in the form of recurrent neural networks. And we have also seen that at least for the auto-regressive model, the further we predict in time, the more difficult it gets. And well, spoiler alert, latent variable models are clearly not robust toward this problem of error accumulation. It holds true in general that forecasting longer periods in time is complicated. And we have seen how neural networks, this is what you have briefly seen in this notebook, are easy to set up as an autoregressive model. And there are many papers which try out neural networks in the setting and conclude that they work fairly well. And this is also my experience. There are much more advanced architectures for neural networks for time series data or for sequence data. However, well, getting these to work so that they really outperform the simple feed-forward neural networks is not necessarily a trivial endeavor. But I'm jumping ahead one more time, so time to pause for a minute before we move on with language models. And this is what we do in our next session.